Hello, this is Jason Kendall and welcome to the next of my introductory astronomy lectures, doing more on the fundamentals of telescopes. So here we go. The most important aspects about telescopes are their ability to discern things. And so the ability to discern things is related to what we call resolving power or resolution capacity. So we can see in this very funny little picture taken by someone at the European Southern Observatory that this baby might be much larger than a 5-meter telescope or a very large telescope at the European Southern Observatory. But we know that babies don't come in the sizes of incredibly large telescopes, so we must be doing something with angular size and we must be doing something with resolution. So the angular size of an object is something we really got to look at and understand. And the angular size is not the physical size. The angular size is how big something looks, and it's just how big it looks. But that's dependent both on its actual size and its proximity. So let's go back to our 10th grade or 5th grade algebra class or trigonometry class, and we actually take this definition of an angular measurement called the tangent. And the tangent of an angle for a right triangle is simply the size of the object, when we're looking at a right triangle, the size of an object compared to its distance. So the tangent of the angle is, assume something standing straight up and down and how far away it is from you. The tangent of the angle from the bottom to the top of that thing is the size that we perceive it to be, is the size of the thing divided by its distance. The tangent of the angle that subtends is equal to that ratio. So what do we mean by that angle then? And we're going to really play around with this thing because the angle that theta angle, the Greek letter theta, is very important to us. All right, so the tangent of an angle may be thought of in that original way, which is the distance to the object. Maybe it's a flagpole, maybe it's a tree, maybe it's a really, really, really large object. But if it's close, the angle will be large. And if it's far, the angle will be tiny. So let's actually look really carefully at this thing for just a second. And where do we get tangents from and all that kind of stuff? So first, if you look at this diagram carefully I've got here, the diagram itself, it inscribes a circle. So we've got the radius from the center of the circle to the circle. That's called the radius, of course. And we can take one radius here and then we swing the radius up and we have an angle that is taken out of the circle. Now, the tangent of that angle is a piece of the radius, not the entire radius, but a piece of the radius, which I've here described as a dashed blue line. So that's the distance to the base of it. Now then, we can then go from that dashed blue line up to the circle, and then the hypotenuse is the radius. So we've got the adjacent, which is a segment that's adjacent to the angle. We've got the length of the segment that's opposite the angle, and then we've got the hypotenuse. So these are all trigonometry, which is all based on angles around circles and right angles. So the right angle is between the opposite and the adjacent, and the hypotenuse is the radius of the circle. So the tangent of the angle theta is related to circles. So let's let now this angle theta well, let's define two other things before we do that. The first one is, let's say, okay, so the two radii for the angle theta touch the circle at two places. And so we may look at that as a length across from the place where the two radii touch, and that's the green line. That's like a straight line, so it almost looks like an equilateral triangle, but it's where the two radii touch the circle. And then we can look at the actual chord on the circle, which is the red line that is on the circle itself. So these three things are three separate lengths. Now, what happens if we let the angle theta get really, really small? Well, the dashed line gets really close to being the entire radius. The hypotenuse is always the same. The apparent height looks smaller and smaller and smaller, and the blue line going from the bottom radius up to the other one gets really close in size to the green line. And it also gets really close in size to the red chord going on the circle itself. So the blue vertical line, the green cut, and the red chord all get very close to each other's lengths as the angle theta gets smaller and smaller and smaller. All right, so now we're going to define the concept of a radian. And a radian is simply take the radius of a circle and put it on the circle. So we've got the radius, so what is that angle? We can define the radian as an angular measurement. We tend to think in terms of angles as like 360 degrees around a circle, but we could instead say, what is the angle subtended by the radius on the circle? And that's always the same for everything. For every circle, it's always that same thing. So we take the radius of the circle and we put it on the circle, and that subtends some angle, and we define that to be 1 radian. All right, well, that's a pretty big angle. It's pretty close to 60 degrees because there are 2 pi radians around a circle. All right, so if 2 pi radians is the same as 360 degrees, but we want to go look at really small angles. So we know there's 60 arc minutes in 1 degree from our way first episode, and we know there's 60 arc seconds in 1 arc minute. So how many arc seconds are there in a radian? There are 206,265, and we saw that before when we were talking about parallax. So this is kind of a redo of parallax for just a second. But we could say there are 206,000 arc seconds in 1 radian. Well, let's make our angle so small that we're only measuring it in individual arc seconds or even arc minutes. Those are really small amounts. So if we measure our angles in arc seconds or arc minutes, then the angle that's subtended is really tiny, and the green line that's on this diagram is very close to the red chord. And so you can almost not tell them apart. Once we get to that size, then actually when we have very, 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 very tiny angles, then we can approximate the length of the chord to being the actual physical size of it, which is the length of the chord is the physical size. And that physical size at some distance is the approximation we're looking at is equal to that the angle in radians. So the physical size divided by the physical distance, and we're approximating the physical size, which is actually straight, but we're approximating it by a really narrow, tiny curved surface, which is the red line here. So again, the angle in radians, which is really small, can be approximated by the size divided by the distance. So the tangent of an angle, when it's really small, is approximately the angle itself, so long as we're measuring in radians. Okay, so how does this work out and what can we use it for? So let's say we have the angular size of something. Pretend we're looking at a football. A football is about 12 inches across. Strictly speaking, it's about 11. And if we take that football and we pushed it so far away that it's about 1 arc second in size, then it's 39 miles away. That's really tiny size. It looks really small. So that has a small angular size. When something looks small, but you know it isn't small, we know the angular size is small. Now, if we took a football and brought it straight in front of your face, it would have a large angular size. That doesn't change the physical size of the football. It changes your perception of it, how big it appears to you. So the bigness appearing to you is what we call the angular size. The actual physical size and how big it appears to you depends on how far away it is from you and how big it actually is. So to make a football have an angular size of 180 degrees, it needs to be so close to your face that it fills up your entire vision. And that's the angle. But then we can't use the small angle formula anymore. It doesn't work. So we really care about things that are really far away because stars are very far away. So that helps us. In this sense, then, a football, which is about a foot across, placed 39 miles away, will be and have an angular size of 1 arc second. All right. So let's see, we're going to look at that for just a second. So angular size, we're going to put that aside for a second and look at the nature of what we call resolving power. So telescopes have, one of the key characteristics of any telescope is actually to be able to resolve things. We want to make out a star from a planet, or we want to see the curlicues of the gas inside of a gas cloud, or we want to make out one star cluster from another in a distant galaxy, that kind of thing. So that's called resolving power. We want to resolve two things that are separate, that are known to be separate, but if they're not resolved, then they're smeared together. So let's see what that works out to be. So resolving power is one of the most important things, and it is limited because once you send, because of diffraction, because the way light diffracts through a boundary. Once you send it through some opening, light starts to diffract and it makes it less smooth. So we can have all this light coming from light years from this distant thing, and it's all undiffracted. As soon as it goes through the aperture of a telescope, it starts to diffract around the boundaries of the aperture of the telescope. That even happens when you hit it off you don't even have a tube for the mirror like research telescopes, and just hits off the mirror itself. The physical size of the mirror itself then starts the diffraction process. All right. So let's look at some examples, and we're going to look at something that's like 10 arc seconds, 10 arc minutes, 1 arc minute, 5 arc seconds, and maybe 1 arc second resolution. And I'm going to play around a little bit here just to give you kind of a feel for it. And I took some images. I took an image of the Galaxy M31 with iTelescope. It's a wonderful service that's a paid telescope service, so if you want to go investigate, please do. And what I did is I then pretended that the resolution was only 10 arc minutes. And that's about what you see with your naked eye. So if you were to look up in the sky at the Andromeda Galaxy, and it's a really dark night, you'd see a fuzzy patch in the sky. And what you're seeing on the screen here is that kind of resolution, as bad as your eye can be. Now we're going to go to 1 arc minute resolution. It's slightly better resolution, and that might be what you get with a good pair of binoculars. Okay, so now let's bring it down again. And if we have 5 arc second resolution, 5 arc second resolution is about 12 times better than 1 arc minute resolution. So now we're much better than what you can see with your eye. And we're starting to make out smaller and smaller features. They're not so smooshed together. And finally, when we get to 1 arc second resolution, which is really good, and really good. I don't even know if this is actually 1 arc second resolution, but I'm pretending that it is just for example purposes. Now we can distinguish gas clouds inside of the Andromeda Galaxy. We can distinguish distant stars that are still in the Milky Way. We can see faint things that don't get blended in with other things. So the resolution of an object allows us to separate things. So if we start again from 10-minute arc second resolution, it's really fuzzy, and then when we get down to 1 arc second resolution, it becomes much clearer, and things that are closer together are separated. All right, so that resolution happens because as light goes into an aperture, it diffracts. So the larger your aperture, the less the effect of this diffraction. But diffraction limits the resolution of all telescopes. It doesn't matter what they are, whether they're Hubble Space Telescope, some big telescope, some little telescope. Diffraction is the limit to the telescope. So what is this diffraction limit? And it's because if you have a telescope with a circular aperture, you get rings around an object. You get a bright central peak and then rings that surround it. And these rings are called Airy disks. And the Airy disk is, of course, named after Sir George Airy, who discovered it and modeled it mathematically. Well, he didn't discover it. He modeled it correctly mathematically in 1835. So let's say that you have 2 stars and they're coming in the light. You want to distinguish them because maybe they're a really cool binary star that are orbiting each other, and you want to really see their orbital motion. So you want to distinguish these 2 binary stars. So when the light from the 2 stars enters your telescope, the circular aperture of a telescope, it starts to make these airy disks. It creates them by the time it gets to your detector. You can't do anything about it. You've got the airy disk of the 2 stars. Well, let's hope they're far apart. Because if the 2 stars are not far apart, then you can't distinguish them. The best you can do is when the peaks are outside from each other and the first ring of the airy disk overlaps the edge of the center of the airy disk of the peak of the other. So the first ring of the airy disk goes across the bright central peak of the other one. And so that's just being able to tell the 2 apart. And if you look at this diagram, we have 3 different flavors of that where there is some darkness between them. The other 2 do not show any darkness between them. So you can't tell if it's 2 stars or if it's like an oblong peanut-shaped object. So when the 2 airy disks overlap, that's when you're getting what's called the diffraction limit. So the diffraction limit for a telescope is kind of an arbitrary definition. I mean, you could play with it in order to get a better resolution. You could pretend that on this diagram that you see here, that the middle one is actually 2 stars, but you really wouldn't be able to be sure. So we're going to call this thing the diffraction limit, and it'll be specifically the Rayleigh criterion. And the Rayleigh criterion is this: the angular separation that you see them to be, which is theta, is equal to 1.22 times the wavelength of light that you're using divided by the diameter of the telescope you're using. And we're assuming a circular aperture to your telescope. And the 1.22 comes as a result of it being a circular aperture and creating rings. Now, if we had a flat slit or a box of some kind, it would be a different number out front. But telescopes tend to be circular, so therefore we get a 1.22 there. And the key is that the wavelength of light is dependent. So short wavelength means smaller, where you can resolve smaller smaller angles. If you have a bigger diameter, then the number is smaller also. So you want to look at short wavelengths and big diameters and use a big diameter telescope in order to get to your diffraction limit. All right, so for as an example, the Hubble Space Telescope, it's up in space. It can look at visible wavelengths, so a typical bluish sort of greenish visible wavelength is about 500 nanometers. The diameter of the Hubble Space Telescope is 2.1 meters. So therefore, if we plug it into this Rayleigh criterion equation, we get that the angular size, the diffraction limit, is about 3 times 10 to the minus 7th radians. Remember from the beginning, we're looking at really small angles, so this is good. And that means about 0.06 arcseconds. So the Hubble Space Telescope's diffraction limit is 0.06 arcseconds. So if something is, say, 0.01 arcseconds or 0.0001 arcseconds, the Hubble Space Telescope isn't going to be able to resolve it. So if we then say, let's play around with it and say, let's say we could point the Hubble Space Telescope at the moon to try to see the flags left by the Apollo missions. All right. The moon's about 2,000 miles across, it's about a half a degree wide, so therefore that's 1,800 arcseconds in the sky. And since it's 2,000 miles across, in 1,800 arcseconds, that means the Hubble could, in theory, resolve something as small as about 330 feet apart because of diffraction limit. All right. The flags of the Apollo mission are about 4 or 5 feet wide, so we're never going to resolve the flags from using the Hubble Space Telescope. Also, if you were to mention this to John Grunsfeld or anybody else on who deals with the Hubble Space Telescope, or Mike Massimino, who's this really big guy over at the Intrepid Air and Space Museum, who's actually done Hubble servicing missions, he would want to throttle you, because if you pointed the Hubble Space Telescope at the moon, you'd blow out the instruments, because the instruments are incredibly sensitive and designed for low light, not for the brightness of the moon. So we can't see the flags on the surface of the moon even using the powerful Hubble Space Telescope, because the diameter of the Hubble Space Telescope simply isn't big enough in order to get the resolution we're looking for. All right, so we can't do that, and what's even worse is that let's say we took the Hubble Space Telescope and instead, well, there's 2-meter telescopes on the ground, right? You can build a 2-meter diameter meter and a 2-meter diameter telescope on the ground and point it at things, but you will never get 0.06 arcseconds on the ground. And that's because at best on the ground, we get about 1 arcsecond from the ground. And why is that? It's because we got the air. The air, we talked about this last time with the refraction of air. When light goes from a vacuum into air, it starts to refract. But yet the air is turbulent, meaning that there's pockets that have a little bit more water vapor, a little less water vapor. They might be drier, they might have a different temperature. So that changes the index of refraction of the air, and these sizes of these bubbles in the atmosphere range from about the size of about a basketball to the size of a car or so. And so the sizes mean that as the light travels through the atmosphere from a distant star, it's been going in a straight line for light years, maybe 1,000 light years, say for star Betelgeuse, 600 light years. It comes in the atmosphere and then starts to refract and bend, and its path changes as it travels through the brief bit through the atmosphere to come to your telescope. And that makes the star's image wander. And that's where the twinkling of stars comes from. Because as the image wanders, if you're looking at stars without a telescope, the starlight comes into your eye and falls in between the detectors, which are called the cells of your retina. And so you see a twinkling in your eye. Now, in a telescope, we don't really care about that because we have a detector, and the detector has pixels. And so it wanders around on the surface of the pixel, spreading the image. So if we look at through a telescope with a detector or a camera, the image spreads on the surface because of the variable refraction that the atmosphere has as the light's coming to us. And we call that spreading of the image seeing. And seeing, if seeing is bad, meaning it's kind of turbulent, there's lots of moisture in the air, there's clouds in the sky, maybe there's high clouds, so that would be the seeing is bad and it looks schmutzy. Yeah, you might be able to see some stars through very thin cloud layer, but you wouldn't want to try to take detailed images of some faint star cluster or some faint nebula because it'll be out of focus. Why will it be out of focus? It'll have poor resolution. Why will it have poor resolution? Because the seeing is bad from the index of refraction changing through the sky. So as we've seen, the resolution is our big thing. It depends upon the angle that we're looking at, and typically the size scales, the angular size scales, are less than a few arc minutes that we care about, and maybe we're looking at something that we're looking at for arc seconds. And so angular resolution is really key. The only way we can get better angular resolution is building bigger telescopes. If we build bigger telescopes, we better build them in space, because if we don't build them in space, we have to contend with the atmosphere on the ground. And that's called seeing, and that is not a diffraction limit, it is an atmospheric limit. Now there are strategies to get around this, and we will look at those next time. See you soon.